This is an interesting lesson where you will learn how to calculate the work done by a variable force, because so far you've been finding work done by a constant force that does not change when we use it in the equation work done as a dot product of force and displacement. So let us create a small setup where we attach a mass m to a spring that has one of its ends attached to a rigid wall. Now, if you pull the box to the right, the spring will elongate, and what we know from experience is that the spring would tend to pull it back into its normal position with a certain force. And this force is also often called the restorative force, because what the spring is trying to do is to restore its normal position or come back to its normal position. Also, as you pull the mass further to the right, the spring elongates with it, and this restorative force increases further. So, in a way, more the pull, more the displacement of the box to the right, more the force exerted by the spring to the left. Another thing you must note is that while the displacement is to the right, the force in the spring is to the left. So this force is given by the formula F is equal to minus kx, where k is the spring constant. That is, you could say it is a measure of the stiffness of the spring. So larger the value of k, more the stiffness and more the force with which it will pull back the mass. And x here is the displacement of the mass to the right or the left. So you can see that this force has a linear relationship with displacement. And this equation was given by the great scientist Robert Hooke in the 17th century. Also, an important thing to note is the negative sign here, which tells us that the force always acts in a direction opposite to the displacement. So, when you move the mass to the right, or the displacement x is to the right, or a positive displacement, you know that the spring will pull the mass to the left. That is, the force is acting in the opposite direction. Likewise, if you push the box to the left while the spring gets compressed, it also at the same time pushes the mass to the right. So again, the force and the displacement are in opposite direction. In other words, the two vectors, that is the force and the displacement, are always 180 degrees apart. Okay, so let's say this was the position of the mass at rest. So this is the 0 position, and then we pull it to position x is equal to 2 meters over here. Also, what is known is the k value for the spring is 4 Newton per meter. So the force on the mass at this point would be minus plus 2 meters into 4 Newton per meter, or minus 8 Newton. So you can see that while the displacement was positive 2 meters, the resulting calculated force is minus 8 newtons. Likewise, if the spring was compressed by the mass in this direction, and let's say the displacement was minus 0.5 meters, we can calculate the force acting on the mass on account of the spring is equal to minus 4 newtons per meter multiplied by minus 0.5 meter displacement, and this therefore equals 2 newtons. And in this case again, while the displacement is in this direction, the force due to the spring is in this direction. That is, they are opposing each other. So that takes us to the next question. How do we find the work done by this force if this force keeps changing or is variable? Because so far we've been calculating work done by a constant force only. To find this, let's consider the position of the box at a displacement xi. That is, this is the initial position, and then the final position is xf. Now, we know that as the box moved from xi to position xf, the force on it kept increasing. So let us slice up this entire segment into very small lengths of delta x. Now, if we look at, let us say, this segment, since it is very small, we can assume that the force does not quite change when we move from one end of this tiny segment to the other end. And this would be true for any segment. So let us mark the changing force as F1, F2, F3, and so on right up to the end. And now let us find the work done in each segment, starting with the very first segment. Well, now it seems a lot simpler. In this segment, the displacement is delta x and the force is F1, and they are 180 degrees apart. So the work done in this segment is delta W is equal to F1 dot delta x, which equals F1 delta x cos 180, which equals minus F1 delta x. And we could apply the same logic to each of the other segments as well. So in segment 2, work done is minus F2 delta x. In segment 3, it is minus F3 delta x. And all the way up to last segment, let us say it is segment number n, it will be minus Fn delta x. So if you add up all these quantities of work done in each segment, you can get the total work done between x1 and xf. And how do we add up these segments, or rather the work done in these segments? Well, integral calculus is a wonderful tool to add up all these small quantities of work done, and using the formula total work done is equal to integral of minus f dx as the limit changes from xi to xf, we can get the total work done. Here dx is a very, very small segment, often termed as infinitesimally small, or so small that it is almost near zero. Then putting force F as kx, we get total work done is equal to integral of minus kx dx from xi to xf, which equals minus k integral x dx from xi to xf. And that would equal minus half k x final square minus x initial square. And if you multiply this out, what you get is total work done is equal to half kxi square minus half kxf square. So in this particular case, total work done would be a negative value, or the spring force did negative work. However, if the box had moved, say, from here to here, the work done by the spring force would have been positive. So if you examine this formula for a few minutes, what you'll find is that the spring force does positive work if the box ends up towards a relaxed position, that is x is equal to 0, but it does negative work if it ends up farther away from x is equal to 0 position. Also, if we take xi, or the initial position, as 0 and drop the subscript f here, or just take the final position as x, we can say that the work done is equal to minus half kx squared. So you could use this formula in general, but if the problem specifically mentions that the object is displaced from its rest position, you could simply use this formula. So this is a particularly useful lesson when you want to find work done by a variable force. However, you must go through this playlist to really cement your understanding around work, power, and energy. And like always, if you like this lesson, do give a thumbs up. That'll be helpful. And I will see you in the next lesson.